began in 1930s, when Swiss astrophysicist Fritz Zwicky measured the motions of galaxies and realized that even after he accounted for all the stars and gas, something seemed to be left over. Massive clumps of unseen material yanking galaxies around at high speeds. What scientists believe this to be is dark matter, to which they agree to be an undetected form of mass that emits little to no light, but whose existence they infer from its gravitational influence on galaxy clusters. Still, not knowing what dark matter is today, we can tell you exactly what it is not made of. It is not made of ordinary atoms that make up you and me. Dark matter is not antimatter because we don't see the gamma rays produced when antimatter annihilates with matter. There is a number of different theories on what dark matter could be. Dark matter could be WIMPs, or also known as weakly interacting massive particles, which are the subatomic particles which are not made up of ordinary matter and are weakly interacting because they can pass through any ordinary matter. Another theory on what dark matter could be is neutralinos, which are members of another set of particles which has been proposed as part of physics theory known as supersymmetry. This theory is one that attempts to unify all the known forces in physics. Neutralinos are massive particles. They may be 30 times to 5,000 times the mass of the proton, but they are lightest of the electrically neutral supersymmetric particles.
The next topic we'll be covering is dark energy, also known as the solution to the mystery of the universe's expansion accelerating. Dark energy is the name given to a strange entity that appears to make up most of the mass energy density of our universe. This mysterious energy is pushing apart our universe, and its identity appears to be at least as elusive as that of dark matter. The usual wrong way to explain the reasoning of dark energy causing the expansion of the universe to accelerate is to point out it has negative pressure, the same pressure that in a balloon or an inflated tire. But negative pressure, or tension, is more like a stretched string or rubber band, pulling in rather than pushing out. This explanation isn't wrong, but not the slightest bit of help in bringing people to any real understanding. The right way to explain this would be not to mention pressure at all, positive or negative, for cosmological dynamics. The relevant fact about dark energy isn't its pressure, it's that it's persistent. It doesn't dilute away as the universe expands, and this is even a fact that can be explained by saying that dark energy isn't a collection of particles growing less dense as space expands, but instead is, according to our simplest and best models, a feature of space itself. The amount of dark energy is constant throughout both space and time, about 100 millionth of an erg per cubic centimeter. It doesn't dilute away even as space expands. So the density of dark energy is constant, which means the curvature of spacetime is constant, which means that the universe expands at a fixed rate. The evidence for existence of dark energy. The cosmic microwave background is the thermal radiation left over from time of recombination in Big Bang cosmology. According to the cosmic microwave background, the universe has a flat shape. We know from observing galaxies and clusters that all the matter in the universe only makes up about 27% of the total mass energy density needed in a flat universe. In order to match the observations from the clusters with the cosmic microwave background, we must account for the missing 73% of the mass energy density, which is where dark energy comes in at. More direct evidence for dark energy comes from supernovae observations. A supernova is an immense explosion that happens when a massive star reaches the end of its life, and for a brief period of time, typically a few hours to a few days, they shine as bright as an entire galaxy of 100 billion stars, meaning we can see these explosions in distant galaxies. The explanation theories on dark energy. A property of space. Empty space can possess its own energy, also known as dark energy. Since this energy is a property of space itself, its mass remains constant as space expands. As more space comes into existence, more energy would appear. As a result, this form of energy would cause the universe to expand faster and faster. Similar to Einstein's cosmological constant, but instead of being a force that keeps the universe from collapsing on itself, dark energy would be one that tears it apart, pulls it apart. The quantum theory of matter. In this theory, empty space is actually full of temporary, virtual particles that continually form and then disappear. But when physics tried to calculate how much energy this would give empty space, the answer came out 1 with 120 zeros after it, too big. With a hard-to-get an answer, the mystery still continues. Another explanation for dark energy is that it is a new kind of dynamical energy fluid or field, something that fills all of space but something whose effect on the expansion of the universe is the opposite of that of matter and normal energy. This is known as the quintessence, a fifth and previously known type of fundamental force which fills the universe like a liquid. But if quintessence is the answer, we still don't know what it is, what it's like, what it interacts with, or why it exists. A last possibility is that Einstein's theory of gravity is not correct. That would affect not only the expansion of the universe, but also the way that normal matter in galaxies and clusters of galaxies behaved. But the question would be, if or how could it correctly describe the motion of the bodies in the solar system and still give us the different prediction for the universe we need?